All right, let's start the final session for today. So now we are going to learn about simulation of materials from Andrew. Please take it away.
Thank you for the introduction. Thank you to the organizers for the invitation, and thank you all for your attention today. This would be a lot more effective if we hadn't just had a break with cookies, but I'm offering cookies as an incentive for answering questions and being attentive. And no one wants cookies from some random physicist, but they were made by my wife Shirley, and she's a French chef, so they're pretty good, but pay attention. So today I'm here to talk to you about quantum simulation materials in extreme conditions, and in particular I'm going to be telling you about a recent result that we have more or less focusing on a quantum algorithm, really a full protocol and end-to-end sort of resource estimates for estimating electronic stopping powers that are relevant to inertial fusion target design. I'll allude to, at the end of my talk, some of the other materials and extreme applications that we've been looking at, but this is primarily a talk on that result. And to that end, I'll start by acknowledging my collaborators on this. This is primarily the result of a collaboration with a bunch of folks at Google and kind of affiliated institutions. I myself am at Sandia National Labs as my co-author on this paper, Alina Kononov, but plenty of people on here. Nick Rubin, lead author, Ryan Babish, Harman Nevin, a bunch of folks at Google. All of us working on this recently appeared in Proceedings of the National Academy of Science. There's also an archive link up there. And I'd like to thank, the ASC program, Office of Fusion Energy Sciences, and Sandia for our funding on this. So, okay, getting into the meat of the talk. Inertial fusion is the name of the game here. So I promised in the title of that paper that there'd be something about inertial fusion target design. Well, what the heck is inertial fusion target design? Well, this is a particular approach to inertial fusion that's gotten a lot of press as of late. This is the indirect drive approach that's taken at the Lawrence Livermore National Laboratory, the National Ignition Facility. It's a nice reference to one of their recent results that shows that this is an effective approach to implementing inertial fusion. In particular, they're able to achieve ignition. What does that mean? Well, in this particular platform for inertial fusion, you have a bunch of lasers that are essentially, again, indirectly driving a target that contains some deuterium and tritium fusion fuel. That indirect drive is a bunch of lasers that are essentially focusing on the walls of a high Z metal Hall room that you see in the figure on the side over here. And that Hall room gets very hot inside. So hot inside that it starts to radiate X-rays. Those X-rays then impinge on a little fuel capsule that, the walls of which are made of high-density carbon, the interior which contains essentially deuterium and tritium fuel that fuses. And ignition in this approach is basically you drive an implosion that essentially collapses that little ball containing deuterium and tritium. And at some point, you're going to start to cause fusion events in which alpha particles are produced. Those alpha particles are going to start redepositing their energy into the burning plasma, and at some point, essentially the rate at which those alpha particles are produced and redepositing their energy into the plasma will exceed essentially conductive and radiative losses away from the target. You get ignition, and you get a Nature paper too. In any event, this is the type of approach that people are looking at. This is the type of approach we're going to kind of be studying in some sense. We're going to be looking at essentially the resource estimates for evaluating a particular property of relevance to the target design of something like this. But it's not just approaches like that indirect drive approach that's taken at Livermore. We also have fusion concepts that we work on at Sandia. This is the Z facility at Sandia. This is the arcs and sparks picture taken by Randy Montoya. And this is exemplary of the sort of extreme environment that I alluded to in the title of my talk. What you see on the other side of the slide right here is essentially a sequence of 3 images from a hydrodynamic simulation of a maglev implosion. Maglev is magnetized liner inertial fusion. This is a particular approach that's studied at Sandia and actually uses one of the lasers from an early stage of the NIF facility in order to essentially preheat a deuterium plasma and essentially drive a collapse and implosion with strong current delivered over 10 nanosecond time scale. In order to design experiments like this, we need to be able to essentially model the behavior of these materials as they essentially go from kind of their ambient conditions sitting around in the lab all the way up to, again, thermonuclear burn. So it turns out that the instabilities that develop on the way to ignition, so not, when you already achieve the thing that's burning, but, kind of on the way towards it, are what make this actually a very difficult problem. In particular, it's a material science problem in some sense, and this is, I think, something that we're all much more familiar with thinking about in the context of quantum computation. So this material science problem is complicated by the fact that it's very difficult to actually realize materials in the conditions that are relevant to fusion in a laboratory. You need facilities like Z, you need facilities like the National Ignition Facility in order to actually make little bits of matter that achieve these states, and that's very expensive. These are multi-billion-dollar facilities that are centered at DOE labs. They go off about once a day, this sort of thing. It's very rare to get access to them. We want to be able to design these targets, but it's very expensive to kind of go through this entire design cycle, so we use a lot of simulation. Again, we need to simulate materials in extreme conditions. I mentioned that there's this idea that there's an intermediate regime basically between where your target starts and thermonuclear ignition that's kind of hard or difficult to design around, and that's this warm dense matter regime that's in the middle of this chart on my slide right here. So this is a, I guess, two-dimensional plot, logarithmic in both dimensions, density and temperature. So this is spanning a fabulously wide array of thermodynamic conditions. And warm dense matter is essentially this intermediate regime in between kind of where the fuel starts and thermonuclear ignition. This is also where actually the target spends most of its time during this implosion. And you might be thinking to yourself, well, geez, like that's awfully hot. Isn't that classical? Isn't this trivial to compute on a classical computer, yada, yada, yada? And it turns out, no. The thing that typifies warm dense matter and makes it challenging is it's essentially the regime in which degeneracy and thermal excitation are both kind of comparable. It's one way of thinking about it is that the temperature is on the order of the Fermi energy of the plasma. So you do actually have quantum effects, you have chemistry, you have things like this that are kind of rare and weird and very difficult to manage because, again, in order to design one of these experiments, we need to be able to basically predict how our targets are going to behave over this fabulously wide range in conditions. So how do we actually deal with this problem? Well, let's start with a particular property that we need for these types of simulations, and I'll tell you how we calculate them on a classical computer, and also evaluate it experimentally. Stopping power is kind of the main thing that I'll be talking about today. It's the focus of this publication that is kind of centering the talk. And stopping power is actually a relatively straightforward thing. You have a target, you have a projectile, you fire the projectile through the target, and you measure the energy that is lost as basically that projectile passes through the target. Stopping power is commonly rendered as essentially a velocity-dependent quantity, so you want to measure essentially the average force that the target is pushing back on the projectile with as a function of the velocity that that projectile is going into the target, right? The energy loss is due to collisions with things like nuclei, electrons, and light. We're going to be ignoring nuclei and light today, actually, because they can be ignored in this particular regime. The dominant kind of loss mechanisms for stopping in the particular conditions that we care about today by a couple orders of magnitude are due to the electronic excitations of the system. So this is actually an electronic dynamics problem, an excited state electronic dynamics problem that, crucially, it still, kind of is hard in this sort of temperature elevated regime. One final thing to note, stopping power, somewhat frustratingly, is actually a force. You'll be seeing me talking about, essentially an average force pushing back on things. It's not a power. Unfortunately, I don't know, naming conventions that have existed for over a century. So the particular thing we want to use our quantum computer for is to calculate this average force. How do we do this from first principles on classical computers? Well, we simulate the dynamics of that projectile on about a nanometer, order nanometer length scale, and an order attosecond time scale. So this animation that you see here is a proton passing through a deuterium plasma at conditions that are relevant to this warm dense regime. I'll play it again just because, I don't know, a lot of computer time went into this, but yeah, pretty pictures, right? In any event, the Hamiltonian that governs all this is, again, the same standard one that we're used to in electronic structure theory as it applies to chemistry and material science, actually. So a Hamiltonian that we all know and love. Now, I think Aram made the comment about kind of knowing your enemy here, and our enemy with respect to classical simulation is time-dependent density functional theory. It turns out that time-dependent density functional theory, which is the method that we use to calculate these stopping powers, is one, relatively inaccurate, and two, actually fabulously expensive, in spite of the fact that it essentially has mean field accuracy. So you don't necessarily need to understand the contents of this particular figure. This is a set of stopping curves for essentially an aluminum plasma at 1, 10, and 20 electron volts for essentially a proton stopping. It was generated by my colleague Alina Kononov. The thing to take away from this is not necessarily we want to generate this fancy figure. It's that it took about 250 million CPU hours to produce this figure using a $174 million computer that used to be sitting somewhere in Los Alamos, New Mexico. We don't use those expensive models or calculations to do this hydrodynamic modeling and target design, but we do use them to check the models that are actually used in that process. So someone who is developing a model that would go into one of these codes would come out to me or Alina and say, hey, we'd like to check what we're putting in this code with some high accuracy sort of classical quantum simulation, let's say. And after about 18 months and a large expenditure of resources, they'll get a fabulous figure like that. So one of the limitations of this, though, is that the accuracy of these methods is actually rather difficult to assess. So on the left side of my slide here, I have a figure taken from a recent paper by Lena Kononov et al. In MPJ Computational Materials that's essentially doing a comparison between a couple of different TD-DFT calculations and an experimental database for aluminum stopping power in ambient conditions. And what you can see here is essentially that the theory agrees actually pretty well with experiment up to some limitations, right? But this is in a particular regime in which it's very easy to create targets of aluminum that we can blast over and over again with a proton beam and measure this, right? This is taken from an exhaustive database that people started, I think, assembling in something like the 60s or 70s. So we know that it agrees well when it agrees well, but we don't even necessarily have a great understanding of why it agrees well when it agrees well. Which is, say, on the right side of my slide here, I have another figure taken from this paper in which we're comparing essentially a state-of-the-art sort of finite size error model that was used to essentially estimate the size of errors on these types of calculations, and the actual size of the errors on the calculations are the blue data that scatter all around it, which is to say that even kind of the conventional wisdom for error modeling in this regime is challenging insofar as empirically this particular approach doesn't appear to work. So we'd like to have something like a quantum computer that can at least give a systematic accuracy that we can kind of control and assess, because it's difficult to get it out of these types of simulations. You might be asking yourself about why we can't just do experiments, and of course we actually do experiments, or more accurately, this experiment was done by a group from MIT operating at the Laboratory for Laser Energetics at the University of Rochester. This is just to give you an idea of the sort of measurements that are done and how we actually validate some of these models. You basically make a small fusion capsule or something that looks like a small fusion capsule, you drive an implosion, and you take the protons that come out of that process, this particular reaction that you see underneath the figure right there, and you pass them through essentially a beryllium plug, in this case, that is isochorically heated using essentially the same laser that we use to drive the implosion, that's used to generate X-rays. It's a whole complicated process. At the end of the day, you're able to measure essentially the energy loss through this degenerate plasma, and you get something that looks like the figures on the bottom right-hand side of my slide right here. We have cold and warm. Warm, the colored data, this is again for a target that's about 32 electron volts in temperature, so that's something like 300,000 Kelvin or something like this. It's hot, but it's also very dense. The colored data here correspond to two different experiments, two different shots. You can see that they don't agree with each other, so that seems like a fairly significant source of systematic error. Then on the right, you see some classical calculations, essentially, and there is some amount of agreement between some of those and some of the experiments. But again, this is one data set, and in point of fact, this is actually one of about a half a dozen data sets that constrain stopping power in this regime. So this is all a very long-winded motivation for saying that a quantum algorithm that could systematically study this could be very valuable. So let's return to developing a quantum algorithm for this. Let's go back to what we were doing with a classical computer. So these first principle stopping power calculations essentially involve us taking our projectile particle, in this case a proton or an alpha particle, and dragging it through a supercell of a degenerate plasma, right? So this arrow V-proj labeled here, this is basically that proton moving through at a fixed velocity. That fixed velocity is the velocity which we want to know the stopping power. And we can look at, as you see on the right here, the work that is essentially done back on that particle as we push it through, or equivalently the average force that's acting upon it. And that's the thing that we're trying to compute at the end of the day, is a big table that has all these different curves in it, right? So we might think that we can essentially do what we would do on a classical computer on a quantum computer, and I'm going to tell you all about that and some of the challenges that essentially arise due to that. But at the end of the day, this is how we do the calculation. Create a box, put a particle in it, move it through, measure the average force on it. How do we do that classically? Again, going back to this know your enemy idea, time-dependent density functional theory takes the form of this system of non-linear time-dependent partial differential equations that you see here, where essentially the nonlinear is induced through the electronic density that has essentially the source of the temperature in it. So, these are finite temperature simulations in which there's essentially, orbital occupancies that are distributed according to Fermi-Dirac statistics. But we essentially just time propagate these forward in time. Using, in our case, we use an extension of VASP that we coded up ourselves that implements a Crank-Nicholson propagator, so a lower order integrator actually. And you can estimate the things that you want. In this case, again, this force, this stopping power, right? Time-dependent density functional theory is kind of the only game in town for these types of calculations insofar as they involve relatively large supercells and relatively many orbitals in terms of the interesting dynamics, right? Some of the challenges of time-dependent density functional theory are also some of its primary strengths, and that's that TDDFT is a non-perturbative theory for better and for worse, which is to say that in some respects, there is a sense in which you could come up with some sort of divine functional for TDDFT that would give you the exact potential, that would give you, essentially exact dynamics for this, but we don't know how to approximate it. And in point of fact, it's very difficult to approximate the exact potential in conditions in which people have been able to actually, kind of study it, right? So this is, again, the enemy that we're trying to attack. So this is the starting point for the quantum algorithms part of the talk, which is to say that, what sort of advantages might we expect to have over essentially these mean field sort of theories relative to, the prospect of being able to do exact dynamics on a quantum computer. Well, this is a table that you don't need to understand in a lot of detail other than maybe to check out the reference paper by Ryan Babish et al. On Nature Communications from early last year, in which we essentially examined the asymptotic costs of kind of the state of the art for quantum algorithms for implementing the exact dynamics in first quantization, and compared them to the costs for doing classical implementations of mean field dynamics. And the somewhat surprising thing that you'll find in this paper is that there's actually a regime for which quantum algorithms for the exact dynamics actually have better asymptotics than classical algorithms for mean field dynamics, or in this, to be a bit more blunt, approximate dynamics. So here, the quantum computer's asymptotics are beating essentially the classical asymptotics of, in some sense, the worst useful classical theory. So, interesting paper, but not necessarily the focus of what I'm going to keep talking about here. So we have this notion, at least now, that there is potentially some sort of win for implementing these dynamics problems over something like time-dependent density functional theory. So we might think that we can just do everything that we would do in a time-dependent DFT calculation, but using our favorite quantum dynamics algorithm that we've been hearing all about all day today, right? It turns out that doing exactly that, there are some choices that you need to make, and making the wrong choices can kind of make things worse. So, for example, we want to study, again, we want to produce a curve like the one on the right side of my slide right here, of either the work versus displacement of the particle or the force pushing back on the particle versus its displacement. So you might imagine just estimating the total energy of the system for multiple time evolutions. Getting essentially the slope of that line using phase estimation or something like this. And of course, the problem that you would run into is that energy estimation is then going to be expensive. You might imagine estimating the projectile force, again, across multiple evolution times to kind of make sure that you can get a good average out of this. And the problem that you would run into there is that the force operator has a large norm or variance, depending on the estimation strategy that you're going to use. Furthermore, on classical computers, we update our projectile position in such a way that it essentially becomes a time-dependent Hamiltonian simulation problem rather than a time-independent Hamiltonian simulation problem. And this just ups the cost attendant to, going from a time-independent problem to a time-dependent problem. So the solution to all this, if you're, kind of following through and trying to make the best choices that you can make in designing a quantum algorithm for this, is to, one, make the projectile an explicit quantum degree of freedom. So it's autonomous evolution under a time-independent Hamiltonian will give you the dynamics that you want. You would then consider estimating its kinetic energy in multiple evolution times in order to kind of circumvent the problem of essentially the cost of energy estimation, right? So this is roughly what we're going to do. And it's worth noting that this is going to involve essentially promoting that projectile particle from kind of a classical point particle to actually a nuclear wave packet. So I'll get into the details of this as such. So I'm going to walk through the different steps of the protocol that are outlined in our paper. Step 0 is essentially to choose a representation of the system. In this case, we're going to be working in first quantization. How do we represent the target and projectile, that supercell material? Step 1 is to prepare the initial state for the electron projectile dynamics. So kind of the usual thing of how do you start your quantum simulation? You need to prepare a state that represents an initial state that you care about. Step 2 is time evolution. Implement that, again, time-independent Hamiltonian simulation. Use whatever flavor of method you want, and I'll compare 3 different methods in my slides. Measure the projectile's kinetic energy as a function of its trajectory is kind of step 3 here. And then step 4 is essentially post-processing. It's taking those sampled outcomes for the kinetic energy loss and using them to estimate the stopping power. So step 0, this is where we start by figuring out how we want to represent this supercell of essentially the degenerate plasma plus this projectile particle. The system is going to be described in first quantization using prior art described in these Baczewski et al. And Su et al. Papers. So essentially these are kind of standard approaches for representing, again, first quantized electron nuclear systems. Each quantum particle here is going to be described by its own register of qubits that encode essentially a plane wave basis, attendant to the equations up there. And the electrons are all going to be treated as quantum mechanical here. We're basically going to have eta registers for each of the eta electrons. And we're going to add 1 explicit nuclear degree of freedom that's going to be the projectile. And we're going to treat all of the other nuclear degrees of freedom classically. So essentially we're going to have some eta plus 1 set of registers that are all going to, again, carry around this first quantized encoding of the electronic system and the nuclear system, right? The reason that we're able to ignore the other nuclear degrees of freedom is essentially one of timescales, which is to say that all the other non-projectile nuclei in this degenerate plasma that we're concerned with, at the temperatures relevant to what we're looking at, are basically not going to move at all. The only thing that's moving fast is that projectile, and that projectile is actually moving about as fast as the electrons, which is to say the electronic stopping power is interesting when the projectile velocity is close to the Fermi velocity of the system. So at the end of the day, this is basically taking prior art on these first quantized sort of simulation algorithms, but with some non-trivial extensions that are included in our paper to kind of incorporate details of the projectile that are somewhat non-trivial, again, relative to prior art. Step 1, then, after we've defined our representation, is to prepare this initial state. So the joint electron projectile system is the equation on top right here, which is to say that we want something that looks like the electronic Gibbs state on the electronic subsystem, and we're going to tensor on that nuclear degree of freedom in essentially a Gaussian wave packet that is well localized in momentum space about the momentum that we care about estimating the stopping power at. So I'll talk about these 2 different factors of the initial state separately. The factor that corresponds to the electronic subsystem, this is, of course, generically difficult to prepare sample from. We've heard a lot of beautiful results in this area today for sort of Gibbs sampling, all this sort of stuff. What we're going to do is relatively straightforward, actually, compared to that, which is to say we're going to start with actually a mean field initial state for Merman-Kohn-Sham density functional theory. And then we're going to essentially generate a canonical ensemble over that mean field reference state that we're then going to draw pure state samples from as our initial states that we're then going to do the electronic dynamics on top of. And the hope is essentially that there's a very quick burn-in some sense that essentially dynamically kicks the system into about the place that we want it to be for the subsequent dynamics for estimating all this sort of stuff. And this is actually roughly what we do on classical computers as well. The only other thing that's maybe worth noting here is that this particular advance relies on some advances for efficiently preparing Slater determinants, again, in this 2023 Nature Comms paper by Baczewski et al. Turning to the factor concerning the nuclear wave packet, this is relatively straightforward. It's just a Gaussian wave packet in momentum space, and it's sharply peaked near the velocity or momentum that corresponds to, again, the velocity of the stopping power we want to estimate. Of course, the variance of that wave packet actually winds up being a free parameter, and we might think that we need to start with kind of, a femtometer scale sort of variance in real space, let's say, to capture a proton. But it turns out on the basis of essentially doing a bunch of classical simulations, we're able to blow up that particle to be about 10,000 times larger than kind of that sort of, Fermi sort of radius of the proton, while still maintaining the accuracy that we want right here. And of course, for actually preparing this, again, we're using prior art. Step 2 is where we get into kind of the choose your own adventure aspect of time evolving the system. We considered 3 different approaches to this: cubitization, interaction picture, and trauterization, with kind of respective advantages and disadvantages indicated below. Cubization, of course, we know how to bound these things, again, building on prior art. Interaction picture actually looked quite promising initially, but for the very specific kind of conditions that we care about here, it actually winds up not being competitive, though there appear to be some conditions where it would be at higher densities. And trotterization, of course, has the usual thing of being hard bound, et cetera, but we hope that it will work out pretty well. Just to give a flavor of some of the, I guess, nuts and bolts that are in the paper, the qubitization counts that we give, of course, are relying on essentially using quantum signal processing to implement the Jacobi-Anger expansion. And our block encoding now includes the nuclear projectile. So this is, again, kind of standard sort of stuff, but with this new detail concerning a projectile. The trotterization resource estimates that I'm going to show you involve some advances to some of the circuits internal to that, essentially involving the inverse square root computation intended to computing the Coulomb interaction. So there's essentially using interpolation QROM and Newton-Raphson for that inverse square root, and there's some nice numbers for getting that cost down in this paper. Otherwise, for the trotter stuff, there was significant numerical testing that went into estimating constants for tighter trotter downs based upon the result indicated right here. Some pretty heroic numerical experimentation done by Nick Rubin at Google. And what else is there to say about that? I guess the resource estimates I'm actually going to show you today are from, again, one of these bespoke eighth order product formulas that I think Raul mentioned earlier in his talk. But at the end of the day, I'm going to show you numbers essentially for trotterization and this QSP sort of qubitization sort of thing. One thing that's worth noting is, again, we're doing all this in a context where we want to produce resource estimates for actually implementing this calculation in a regime where we can't do it on a classical supercomputer. Attended to that, we're using some tools from Google. This Qualtran tool is used to build and profile model of the entire protocol. You see right here essentially different subroutines and their non-Clifford counts, in particular Toffoli counts, for 3 different instances. And essentially the different subroutines, correspond to different things that, we won't really talk about in this talk today, other than to say that with this very nice tool, you can look at this and you can say, okay, this subroutine C4 happens to be the hot one in some sense. This is the one that dominates the runtime. And it turns out that this is essentially a subroutine that involves applying a bunch of controlled swaps to move each electron into a working register when you're applying select. Again, this is for the qubitization approach. So it's a really nice tool. I know it's on GitHub and all this. It's beautiful. Lets you make nice results like this. And getting to step 3, we're going to, again, prepare time evolve. We want to measure something. The thing that we want to measure is the kinetic energy of our particle as it's basically traversing this degenerate plasma. So we looked at 2 different methods for doing that. One is relatively straightforward. Again, this plane wave basis that we're working in first quantization is essentially just directly encoding a distribution over momenta. So you can just measure in that basis and get an estimate of essentially kinetic energy straightforwardly. So you can do that, of course, at the standard quantum limit, just repeating and measuring, repeating and measuring, repeating and measuring. Yeah. But there's also an approach that we looked at, basically this mean estimation algorithm from Kotaria and O'Donnell back in 2023 that gives you essentially scaling with the standard deviation of the thing that you're looking at here. So in this case, we have this nice Gaussian that has this nice well-controlled width, but it also gives you Heisenberg scaling. So you're basically getting like a sigma over epsilon sort of scaling right here. So we compared essentially resource estimates for kind of the SQL approach and this KO algorithm, as we've been calling it. And what you see actually is that the Heisenberg scaling approach for the accuracies that we care about happens to actually be the one, if you're going for really high accuracies, that will of course win. Of course, the Heisenberg scaling thing is going to win as you go to higher accuracies. But for the accuracies that are actually relevant to the calculations that we're doing today, it turns out that the SQL will work, which is to say we only need actually something that's closer to this sort of 0.1, the far right-hand side of my plot right here. So this is all to say that, if you were looking for a higher accuracy observable, you would want to use this KO algorithm, but actually SQL sampling will do quite well for the conditions that we care about and the accuracies that we care about. Finally, we need to post-process these sampled outcomes, and this is essentially where we take some of these large-scale time-dependent density functional theory calculations that we're doing, again, on this giant machine sitting somewhere in Los Alamos. We take those data essentially to construct kind of, I don't know how to put it, something like a surrogate for running this on a quantum computer, which is to say that we're essentially taking the calculation of the force to trajectory, all this sort of stuff, and essentially superimposing the sort of wave packets of the nucleus on top of it and seeing essentially the rate at which we can converge our estimate of the stopping power as a function of its accuracy, right? So, sorry, the number of samples we're taking to drive down the accuracy. Apologies. So on the left-hand side of my figure here, you'll see the stopping curve, the sort of stopping curve I showed you from one of Alina's results right here. And this is essentially generated by, again, taking essentially a mock-up of our classical TDDFT calculations and kind of making the surrogate model that allows us to test the convergence of our estimators and so on and so forth. So this allows us actually to assess directly the sampling costs that we're going to incur in doing this, which is to say that we want to know how many times we want to run the algorithm, and this is how we're doing it. There are probably some things that we can improve for, better to account for the variance due to essentially that thermal distribution over initial states a bit better than we have, but this seems like an honest and reasonable sort of ballpark number. Finally, I'm going to leave you with some resource estimates for fusion-relevant systems. What do you have here? You have a table. On the left-hand side of the table, you see the projectile and target. So you see alpha particles, again, the fusion products, and protons, charged particles passing around. And then the target being hydrogen, carbon, and deuterium. And what we're looking at is essentially increasing numbers of electrons from 28 all the way up to 1,729. And you see Toffoli counts for essentially this QSP cubitization approach and the product formula approach. Again, this bespoke eighth order product formula. And there are a couple of things to take away from here. One is that the numbers are relatively large. I saw some eyes get wide when I pointed to the numbers. Thanks.
They're all order one.
Thank you. If you want a cookie, that's not, yeah, please. Another thing that people always seem to notice when we give this talk actually is that the product formula qubits, the qubit counts actually are higher than the QSP qubit counts, and that's essentially due to the QROM attendant to calculating the 1 over square root sort of thing. So this is one of these things that this sort of resource analysis exposes. But just to put this in really stark contrast relative to kind of where we are today, where we'd like to be, et cetera, I've taken a figure from a recent review article that I wrote with collaborators at Sandia, Tim Proctor, Kevin Young, and Rob Blum-Cahote, in which we looked at essentially kind of some notional, big applications that people would like to use quantum computers for, from integer factorization to molecular energy estimation, again, FOMOCO here, and then this alpha plus hydrogen stopping power number from this particular paper. And of course, these numbers are pretty far out, and the thing to take away from here is that right now the Toffoli counts are about 2 orders of magnitude shy of the state of the art for FOMOCO, so there's certainly room for improvement for even that smallest instance right there. But of course, there's cause for optimism insofar as this is sort of the first time that we've done this sort of thing. Otherwise, it's maybe just worth pointing out the lower left-hand side of this plot is essentially experimental data taken from noisy quantum computers, and we're pretty far away from there. But if you want to learn more about that particular figure, I'd encourage you to look at this particular archive posting because, I don't know, I think it gives a nice perspective on essentially the types of advances that are going to be necessary to continue benchmarking quantum computers as we kind of go from this sort of NISQ era to future fault-tolerant regime. Finally, we're only about 2 orders of magnitude from the state of the art for FOMOCO, but there's some question as to whether it would be useful even if it continued to be that far out. I would say that studying strongly non-equilibrium dynamics of even 28 electrons in a large basis, like what we're essentially proposing here, is classically challenging. I'm not going to say classically intractable because that's just inviting trouble, but it's the sort of thing that we can't do it with TDDFT. Of course, someone might come along and do it with some better method. It'll be expensive to implement, but that's hard, right? Furthermore, even if there doesn't wind up being some certifiable advantage or something like this is still going to tell us something interesting about how mean field approximations, like the ones that we use in these TDDFT calculations, fail, which we can't do right now. So that's useful. And for a classical perspective, to kind of close this out, I want to point out that these calculations, again, they took 18 months on a giant supercomputer, about 10% of that machine. If we take 10% of that 40 petaflop machine for a week, which is about how long some of those run takes, you're talking about 2.5 times 10 to the 21 floating point ops. Now, of course, this is an apples and oranges comparison, but 10 to the 21 floating point ops is actually quite a bit larger than the 10 to the 13 to 10 to the 17 sort of Toffoli counts that made some of your eyes bug out, right? So, of course, apples and oranges, but I think it's worth noting. Finally, I'll close on some kind of ongoing work in the regime of materials in extreme conditions. Because those resource estimates are a little bit severe, we're looking at essentially the extent to which embedding methods can be used to reduce resource requirements while maintaining accuracy essential to answering some other questions in materials in extreme conditions, principally questions in astrophysics and planetary science, actually. So on the left-hand side of my figure right here, I have my slide right here. A figure taken away from a Nature article by Jim Bailey et al., a bunch of folks at Sandia, in which they were essentially measuring the opacity of iron in solar interior conditions. This is an algorithm that we're developing right now. Hopefully we'll have it on the archive in the next couple of months. But we're essentially looking at how we can use quantum simulation and embedding methods in order to improve estimates of opacity in these sort of astrophysical conditions. Finally, this is kind of, I don't know, I started like writing this almost as a joke in some sense, but there's a controversy as to the age of the Earth's interior that is essentially being borne out, in experimental labs around the world. The Earth's interior, the iron, essentially, geomagnetic record, all this sort of stuff. It's very difficult to produce iron in conditions relevant to that in a laboratory and actually measure it. And it turns out if you actually trace through all the mathematics and all the different, analyses that people have done to analyze the conductivity of iron in Earth's interior conditions, there's about a 2 billion year spread in the estimated age of the Earth's interior. Again, another cookie. But in any event, that's another thing that we're developing an algorithm for, is trying to study the conductivity of iron in Earth's interior. And if you're curious in that, I'd be happy to talk more. But I will leave with a slide with my conclusions, and I thank you all for your attention.
Thanks, Andrew. Any questions?
Yeah, hi. I have a naive question about this. So, compared to usually the other type of systems we consider, this seems to be like, so the plasma is not really isolated from the environment or anything like that. So, is a closed quantum system simulation the right thing to model this with, or should you use an open quantum system?
You could use an open quantum system, yes.
Yeah.
To the extent that the system is thermalized and we're sampling over kind of different thermal initial states, that's in some sense capturing that. But yeah.
I see. Okay. Thank you.
Hey, is it working? Yeah, great. Thanks for your talk. So, I guess you were talking about the experimental difficulty of actually working with these systems, like the ones you're trying to simulate. But I'm wondering if it is possible to experimentally work with analogous projectile systems. The first one that comes to mind is like electron mean field. Mean free path in like electron beam lithography through materials that you're working with. And that obviously you're not working with the kind of phase of the material that you are in these extreme conditions, but would that work to benchmark your quantum simulation, quantum simulate with the parameters for like electron mean field, mean free path idea, and then see, oh, my simulation is working for that, so then it must also be working for the more extreme conditions, or is it completely incomparable?
You can certainly learn things about whether your simulation is working more cheaply by looking at targets that aren't so intensely excited. And there are, analyses that you can do to try to essentially scale parameters, things like this, to try to bring your model into some sort of extrapolation as to what would happen if you went to these higher temperatures and pressures. But I would say it's not necessarily straightforward. And when we do that sort of thing in practice, actually, we wind up being surprised by what happens in some sense. So this warm-dense matter regime is especially tricky because it kind of it's hard to do those sort of extrapolations in some sense. So because certain approximations, certain things that you would use to kind of do that sort of scaling fail. And I could tell you more details if you care to know, but yeah, I don't know if that helped. So
no, thank you.
Yeah.
Thanks for the great talk. I was curious about the classical simulations you did. You said you took 10% of Los Alamos' resources, so it's about 4 petaflops per second for about 18 months. Is that a classical bottleneck that you hit on the scaling of that, or the advantage of classical scaling is that it's easy usually to distribute a calculation? I'm curious why you stopped at 10% of the resource.
The job allocation system prioritizes things that use about 2,000 nodes, which is about that. Actually, Numbers aren't quite going through my head right now, but yeah, I mean, basically it's a job allocation system. We could run this. We've scaled it to about half the machine before.
And it scaled decently well out to half the. Okay.
Yeah.
Thank you.
So a question I guess I have is that, you were doing a comparison of these individual simulation methods, but I was just kind of wondering, for your particular problem, do you have some intuition based on the degree of locality that you might be having or the distribution of coefficients a priori, whether cubitization or Trotter would be the better approach theoretically for this? And or conceivably, have you thought about hybridizing different simulation schemes in order to try to take advantage of the best features of both?
I can say that I haven't thought too deeply about it, but I have thought about it in part thanks to talks that you've given. But as for the first question, I don't think that there's a whole lot of structure here that's, if anything, this has less structure in some sense than a lot of the problems that we typically care about, simply by merit of the fact that it's kind of like a liquid-like sort of ordering with the ions and so on and so forth. So that might be something that could help, but...
But, would there be things like distant ions being able to use a dipolar approximation for them, or things like that to simplify, some of the larger examples that you did?
So essentially, is the idea for that to, say, compute 1 over r cubed or something like that when you're...
Because due to approximate screening, if you're interested in just one target, right?
Yeah.
That the rest of it doesn't necessarily need to be modeled necessarily with the same fidelity.
Yeah. And I mean, certainly that's the basic idea behind like fast multipole method or any of these sorts. Yeah. So insofar as, you could adapt those things to this area, yeah, I agree. Albeit I haven't thought deeply about how you would say truncate the accuracy of something like an FMM or something, P3M or whatever, as a function of kind of the distance. Albeit I actually worked on that a little bit in my PhD, so I'm going to talk about. Yeah. So. Yeah.
All right, let's thank Andrew again.
Thanks. If you want the cookies, come gather them.